The calculation is made using the idea of determinant from before. At least this is one way to do it, and I think it's the easiest way to keep track of everything involved in the process. We have a vector u here in component form and a vector v in component form, and we set up the calculation for cross product like this. Now notice the notation for cross product as opposed to dot product, you see, so this is cross product. And we set up our determinant, our little 3x3 determinant like this, I, j, and k across the top. All right, and those are just the items that are involved in the algebraic form of this cross product vector. And then the u entries, the entries of u in component form are 2, 5, 1, and they appear in the second row. And then the v items, the 3, 4, 7 appear in the third row. And now we just go through the process as we understand it. Going across the top, now, it's I times the determinant of, now remember the minors, cofactors idea comes into play here, but we take out the column and row associated with the I, and we're left with 5, 4, 1, 7. So it's I times the determinant of 5, 4, 1, 7. And now remember the sign pattern involved in this determinant operation. It was plus, minus, plus across the top. So it's minus j times, take out column and row, and we have 2, 3, 1, 7, 2, 3, 1, 7. And then it's plus k times, take out row and column, and we have 2, 3, 5, 4, 2, 3, 5, 4. Now let's make the calculations. Recall that to calculate the determinant of a little 2x2 matrix, it's just this product minus that product. So for this one, it would be 5 times 7, 35, minus 1 times 4, 4. 35 minus 4 is 31. So this is 31i. And then here it is 2 times 7, 14, minus 1 times 3, 3. 14 minus 3 is 11. So this is minus 11j. And then over here, 2 times 4, 8, minus 5 times 3, 15. 8 minus 15 is negative 7, negative 7k. So here then, in algebraic form, is the vector, which is the cross product of u and v. That is, it is u cross v. Now let's make the calculation of v cross u. Let's go through this, the commutative idea. Does the commutative property hold under this idea of cross product? Well, not exactly, as we'll find out. But to go through that process, we do this. Now, I've just repeated the u and v vectors in component form up here for reference, and we set up our determinant like this, I, j, k across the top. And now the next row are the entries for the v vector. The v vector is 3, 4, 7. And then the next row is would be the entries for the u vector, and that's the 2, 5, 1. All right, then once again, it is across the top. It's I times, take out column and row, 4, 5, 7, 1. 4, 5, 7, 1. And then minus j times, take out column and row, 3, 2, 7, 1. 3, 2, 7, 1. And then plus k times, take out row and column, and we have 3, 2, 4, 5. 3, 2, 4, 5. And with the calculations, we have, let's see, 4 times 1 is 4, minus 7 times 5 is 35. 4 minus 35, negative 31, I. And then here we have 3 times 1 is 3, minus 7 times 2, 14. 3 minus 14, that's negative 11. Negative 11 with this minus sign makes it plus 11j. And then 3 times 5, 15, minus 2 times 4, 8. 15 minus 8 is 7k. Now, you may notice that these are the same entries, but with opposite signs as the ones that we had before. So it's the same, well, fundamentally, it's just a vector that goes in the opposite direction. And because we have exactly the same numbers here, but opposite signs for all of the entries. And that's why it is that in these two calculations, one of those vectors goes orthogonal to the plane containing the original two, the original u and v. Here's the plane containing them. One of these vectors goes in this direction, and the other goes in that direction. All right, product. Before we start the manipulation and making the calculation of cross product, though, I want to talk to you a little bit about the nature of the result of cross product. I have in my hand a few vectors here. Now, we know that vectors have characteristics of magnitude and direction. The magnitude of each of these corresponds with their length. Okay, so that's no big deal. So direction, though. Now, if I take the direction of these two, and I configure them like this, and let me twist my entire coordinate plane a little bit and show you what I'm doing. You see, these are kind of off kilter from one another. But you know, when I'm talking about vectors, I can move vectors around. As long as I don't change the direction of these vectors, I can move them like this and so forth. And I really am talking about the same vector, am I not? All right, so I can actually then put their initial points together like this. And I can then, by that method, realize that any two vectors sort of define a plane. That is, a plane contains any two vectors. And I can show you the plane. I can take my entire three-dimensional coordinate system and I can twist it like this. And now we see that it's contained within this plane. All right, that's one idea. Now, once the calculation is made for cross product, we are calculating a third vector. And that third vector turns out to be orthogonal to the first two and orthogonal to the plane containing them. That is, all right, I'm again twisting our entire coordinate plane, and now here's the plane containing the vectors, and the cross product will give us a vector which is orthogonal to these two and orthogonal to the plane containing them. And actually, there are a couple of ways of calculating cross product. We're going to look at a u vector and a v vector, and we're going to calculate u cross v, and then we're going to calculate v cross u, and it'll turn out that one of those will be a vector on this side of the plane, orthogonal, and the other will be a vector on this side of the plane, also orthogonal. All the triple scalar product. But triple scalar product is nothing more than, given a few vectors that are presumably not in the same plane, and I'll tell you why that's necessary in just a minute, but given a few vectors, we calculate the triple scalar product as the dot product of one of those vectors times the cross product of the other two. And it turns out that you can rearrange these in any way that you'd like, and the calculation comes out the same any way you look at it. So that's kind of nice. Well, let's look at the situation, and I want to tell you about how it's useful. Suppose we have u, v, and w like this. Now, we can kind of put the initial sides of these three vectors together in a particular way, and we can make a three-dimensional figure out of it kind of like this. The three-dimensional figure could be one that's familiar like this. Now, this is a cube, but it could be a three-dimensional figure kind of like this. Now, this is called a parallelepiped. It's kind of a three-dimensional parallelogram. You see, one face is a parallelogram, and we have a three-dimensional effect going on here with this figure. But the idea is that if we have information in terms of vectors from any vertex, and let's just take a vertex like this, if we have information about that angle and distance, you see, and this angle and distance for another vector, and this angle and distance for another vector, then we can make the calculation for the volume of this figure just from that information, and it's by using this idea of the triple scalar product. Now, I mentioned before that it is simply the dot product of one of these vectors times the cross product of the other two. So it works like this. The volume is vector u dot and then the cross product of the other two. Now, notice I have absolute value here because it's possible for this dot product to be negative, but volume is never negative, so the absolute value here is in place to assure ourselves that we get a positive result. Now, the calculation can be made, it turns out, in a couple of ways. We know how to calculate cross product, we know how to calculate dot product, and we can make this separate calculations if we want to. But there is a streamlined way to go through the process, and it is by using a determinant. Now, we use determinant to make the calculation of cross product, and across the top of our 3x3 determinant, we had ijk. Well, instead of putting ijk across the top of the determinant, just put the entries from the component form of this vector. So it would look like this. Now, this is the determinant of these entries, of this matrix. And these are the entries for the component form of U, and this is V, and this is W. And now, this is the determinant, and this is the absolute value of that determinant with these. This is not magnitude with a double vertical lines. This is a determinant and the absolute value of that determinant. So that's the idea. Now, I'm going to come down this first column here because I see a 0, and that's an opportunity for efficiency, as you recall. But it'll be 1 times, now you take out column and row of the 1, and we have 3033, and that's where this 3033 comes from. And then minus, for the sign pattern, plus, minus, plus. So it's minus 0 times, and you take out column and row. It really isn't necessary for us to determine this because we know a 0 factor is going to cause this radical to go out. But just for completeness here, if we take out column and row, we would have 1033. And that's where the 1033 comes from. And then plus the 3 times, take out column and row, 1333, 1333. All right, and then we have, well, let's see, this would be 9 minus 0, so 1 times 9, 9. 0 times, who cares what that is? It's going to be 0. And then 3 times, let's see, 3 minus 9 is negative 6. So 3 times negative 6 is negative 18. 9 minus 18 is negative 9. The absolute value of negative 9 is 9. So we know then that through this process, the volume of this parallelepiped is 9 cubic units of some kind.